So welcome everybody to the latest edition of the Heidelberg Joint Astronomical Colloquium. And we're very happy indeed to have Daisuke Kawata here visiting Heidelberg for the whole week. He's available for meetings, so please get in touch with Michael Bierman. Put your hand up, Michael. Yeah. If you want to sort of meet him on any topic. So without further ado, I'd like to ask Wolfgang Löffler to give the formal introduction for Daisuke.
Good afternoon, ladies and gentlemen. It's a great pleasure for me to introduce Professor Daisuke Kawata from the Mullard Space Science Laboratory of the University College of London. We actually met for the first time when he was a PhD student at Tohoku University, and I was at the same time a postdoc there. And he made his PhD thesis on chemodynamical simulations of the galaxy, and later branched out in the general field of formation and history of the Milky Way and galactic archaeology. He then spent quite some postdoc periods at Swinburne University in the UK and at Carnegie, switching back and forth, before finally settling at the Mullard Space Science Lab, first as lecturer, then as reader, and finally as professor. In the past few years, he has been a visiting professor at the NRJ in Tokyo, and he is the unofficial science lead of the JASMINE consortium, and very much interested also in what's happening in Gaia Near and in the Hayden missions. So today he will give a talk about the JASMINE mission. So Daisuke, the floor and the audience are all yours.
Yeah, thanks a lot, Wolfgang. Is it okay? Okay. Yeah, thanks a lot, Wolfgang. And it's very nice to be working with him, going back to my PhD time. So it is always nice to have that kind of old relationship with getting reunited and working for the mission. And yes, so that I would like to talk about this Japanese astrometry mission called the JASMINE. And I'm responsible for leading sort of scientific activities for the JASMINE, but principal investigator is Naoteru Goda, who is in NLJ, who is driving this mission for many years. And this mission is finally coming along. So this is a very great pleasure for me to talk about this mission. And also we have a special guest today from the JASMINE team. The Ryo Sawa here is also he's responsible for the data analysis in the JASMINE. And this is a quite complicated data, but he is a sort of a master for the data analysis. And also Paul Ramos here is also inventing that in a way to analyze the JASMINE data and ongoing activities. And here is Yoshiyuki Yamada, also from the Kyoto University, and he's also the same time like a similar length to the Goda-san, principal investigator, and him and Goda-san in fact started this JASMINE mission, and they keep going forward, and now we are enjoying this great moment of developing this project. And also thanks to the Michael Bierman and Wolfgang Löffler, the teams, and he's also Olga, Konstantin, and Erasmus. We are having a meeting and talking about the complication and challenge of the JASMINE mission's data. So thanks for hosting us. And so all the things about the JASMINE, what we're going to deliver our science, we have published this PASJ paper this year. And what I will today talk about a bit some science highlight. And science highlight means it's upcoming science highlight. But it's all, if we want to talk about astrometry, of course, we have to start from the Gaia. And myself, it's as Wolfgang said, and I was a sort of theorist doing a galaxy formation simulation, try to understand the galaxy formation and evolution in a theoretical way. But the Gaia really sort of inspired me to see that. And in fact, the revolutionary data really can change the science. And that's why I'm also interested in JASMINE mission and the future Gaia mission. And myself, it's now spending more time and also the effort to understand the new data coming from the, also coming from Gaia and the JASMINE and the Gaia to make a revolution in science. And it is, Gaia is in fact revolutionizing science in not only the galactic science, but also the stellar science, the cosmology, exoplanet, the whole range of science. This kind of new astrometry mission really gave us the new opportunity and the new science. So the space science mission really can revolutionize the sort of landscape of the science. That's great to do that. So I really wanted to contribute. And our institute and Matter Space Science Laboratory in University College London also contributed to this great mission. And in fact, the CCD detector of the Gaia is calibrated and characterized at the MSSL. So the old CCD of the Gaia went through our institute. And our colleague, Mark Cropper, contributed to the design of the radial velocity spectrograph, and we are part of the data processing team as well. But even with this great mission, Gaia, this is an optical mission, and as you can see, this is not a Gaia image, but it is an optical image. You can see that not many stars in this galactic midplane or center of the galaxy. So there is a limitation in this, even this great observatory, and this is a wavelength and not issue, but it wavelength challenge. And if you go to the near infrared, as you know, that this is a two-mass image, but you can see lots of stars there in the center of the galaxy, and also the midplane. So the going to the near infrared is the next endeavor for the astrometry. So when the Gaia is sort of proposed and developed, Goda-san in NLJ in Japan, he was thinking about that in the near infrared astrometry in even that time. And but it's a near infrared, it's not very easy. So Gaia is scanning the spinning and scanning the sky, image of the sky, and having a precession and rotation. And but the CCD you cannot do that because the CCD you can do the this time delay integration, but you cannot do that in a near infrared detector because if you're using a CMOS, so you have to read the data at every shot. You cannot really transfer the charge. So this is challenging, and one way to do is a step on stairs. So you can take a shot and many shots, and then you can decrease the noise. So that's what he was thinking, and I got this his slide in 2009, and he was quite a big ambitious plan, as you can see in a year at that. And but he had some plan to launch the space mission by Deadpan, Japan, to do the near infrared astrometry. So the nano JASMINE was proposed and in fact built in and wanted to launch around 2010. And but because of the uncontrollable issue, we couldn't launch that. But that was one way to build a science astrometry experience in Japan. So that was quite an interesting initiative. And then after that, he wanted to suggest launch some smaller JASMINE mission. And so the near infrared astrometry mission to only targeting a very center of the galaxy and using 30-centimeter mirror. And then after the 5 years later, he wanted to launch 8-centimeter astrometry telescope and mapping the bulge of the central part of the galaxy and doing astrometry for the stars. And of course, we couldn't do that now, but his dream came true. And it is also very good that he was suggesting these 3 different kind of missions in the size as well. So the Japanese people found that, this size of telescope really nicely fit to the rocket launcher developed in Japan. So they found it, and then, oh, this is a very suitable mission. So let's do that with a launch with this new launcher in Japan. So now this small JASMINE is selected by the ISAS in Japan. And now we think that it's probably we cannot really do this bigger JASMINE. So we now change the name of the small JASMINE to JASMINE. But this is happening. So this today I'm talking about this small JASMINE in a concept in 2009. And maybe the bigger JASMINE is now it's sort of a transfer to the effort to the transfer to the Europe, and the Gaia concept is now developed in the Europe, and I will touch that in the end of my talk as well. So we'll talk about this JASMINE, and JASMINE is now selected by the ISAS and JAXA, and the full name is Japan Astrometry Satellite Mission for the Infrared Explorer, and this is a near-infrared astrometry, and also, as I said, we reduce the noise by taking many images of the galactic center region, and so that we can get the time series photometry as well. And so this is 36 centimeter diameter telescope and 3 years mission. And our wavelength range is called HW, which covers 1 micron to 1.6 micron. And this, it's up to the 14 magnitude of the stars. And these old stars will be will follow up with the Subaru telescope in Japan, and this effort will be led by the Shogo Nishiyama in the Miyagi Education University. And so this JASMINE nicely fit that this Japan's Epsilon rocket, and so that's why that JASMINE selected it nicely fit with the rocket, and so this. We called M mission of the Japanese space satellite mission. So we have 2 main science goals for the JASMINE, and JASMINE the astrometry mission, but we also found that, and our colleague suggested that this spec is very useful for the exoplanet science. So the first aim for this main science goal is the Galactic Centre astrometry, to reveal that in central core structures of the galaxies, where we think that all the history of the galaxies are also hidden, and also to explore the formation history of the Milky Way structure like a bar, and which is triggering the radial migration and of the probably of our sun as well. So the near-infrared astrometry is important to really see through the center of the galaxies where Gaia couldn't see that. So that we are looking at that kind of frontier for the astrometry. And at the same time, that this is the time that now the moons and STS-5 and Subaru PFS near-infrared multi-object spectrograph can look at these stars and take a spectra as well. So having this astrometry information from the space is very important. So very nice synergy there as well. And for the exoplanet, we can do the transit of the M-dwarf. M-dwarf is very bright and near infrared. And if we find a habitable zone planet, then JWST and Ariel hopefully still alive. And then we can follow up with them. So we can provide the candidate for the following up observation. So first, I will talk about the main goal of the astrometry. And so this is a target region of the Galactic Center survey for the JASMINE. So we'll target this 1.4 degree field from the Galactic Center, and this is the Galactic Center, and this side is slightly less than that 1.4. It's 0.7 degree and plus minus 0.6 degree. And as you can see from the Gaia image, there's not many stars, or there's 0 stars. None of the Galactic Center stars could be observed in a Gaia. Was observed in the Gaia, and so we will provide astrometry of the parallax and proper motion for the center stars in the center of the galaxy. So we are only looking at this small region. We are 30 centimeter telescope, and not like a Gaia, but we are targeting this quite important region of the galaxy, which is the center of the galaxy. And so this is the data you will get in 2031. And so this is a number of stars we could observe in the JASMINE mission. So this is the main JASMINE field, and we cover that in a bit of the edge of the region as well to randomize the data accuracy. And within this region, we have a homogeneous number of times we observe these stars. And these are stars brighter than 12.5 magnitude in HW. And we have like 15,000 stars there. And we can get that 25 microarcsecond accuracy, like a Gaia-level of accuracy. It's a 20% distance error in the galactic center. And for the fainter stars, it's a distribution, and you can get proper motion accuracy in 125 microarcsecond per year, which is 5 kilometers per second in accuracy of the velocity. So you can get 100,000 stars in the galactic center stars in a very high accuracy of the velocity. So that's what the Gaia will, JASMINE will achieve. And so this region, why we are targeting this region? Because this is a region where the nuclear stellar disk of the galaxy is there. And so the first goal, first science topic for the Gaia, not Gaia, JASMINE, is yes, we are getting that, try to show that and the nature of this interesting object called a nuclear stellar disk in the center of our galaxies. And the size of this is around a couple of hundred parsec. That's why we have this galactic center region targeting our JASMINE mission. And this disk is like a disky, and it's rotating as well. So my colleagues in MSSL, Ralph Schoenrich, he showed that in 2515 from spectroscopic data and apogee, that he showed that this disk is rotating, and so that this is the rotating disk, and this is the distribution of the stars, which is observed by the apogee near-infrared spectrograph, and this is line-of-sight velocity you can get from spectra. So these are bright stars, and then I'm holding that from the center of galaxy, and then x-axis is this axis, but it's absolute value. And then we can get that, and we can see that in the rotation. We did a sigma clipping, but we can see that the rotation velocity of the 50 is, in fact, it's going up to like 70. And this is the image from my PhD student and Philip Stokes' PhD thesis. So this rotating disk there, and so JASMINE will give you a proper motion of this. And why this rotating disk is interesting? Because this cold stellar disk, kinematically cold rotating stellar disk, tell us that when the galactic bar formed. So we believe that from the simulations and observation from JWST now, confirming that from the cold dark matter scenario, all the galaxies started from the very small galaxies, and they merged together with the hierarchical clustering, and then ended up a big galaxies like a Milky Way. But the Milky Way has a bar. So that in some point between here and there, Milky Way needs to form the bar. And when the bar forms is one of the interesting questions, because this is the biggest structure in the Milky Way as well. So the one way to find that, and it is demonstrated by the Junichi Baba in Japan, also from his simulation. And these are face-on image of the simulated galaxies. And this galaxy formed a bar, and then we see that this is the close-up view of the center of the galaxy, and the more gas, the gas of the disk fell into the center because of the bar formation, and they lose the angular momentum, and then make this nuclear stellar gas and make a nuclear stellar disk. So when the bar forms, and the nuclear stellar disk is formed. So if you could know when the nuclear stellar disk is formed, then you can tell when the bar forms. So that's what we can use. Why one way to use the nuclear stellar disk as a sort of tracer of the formation epoch of the bar. And why the bar formation is interesting? Because the bar also can drive the stars to migrate in the radially. In the inner stars form the inner disk, can migrate to the outer disk, or vice versa. going from outward to inward. And the sun, we believe that they formed in the inner disk, and at some point they have to migrate to the current position. So that bar formation may also become a very important factor for the sun to migrate from the inward to outward. So I think it's an interesting thing to think about it. What is the journey of the sun from the inner disk to here? And when the bar starts affecting this journey is a quite interesting topic. So we really wanted to nail down when the bar form. Okay, I probably talk about that. And how to, so we wanted to identify the formation time of the nuclear stellar disk. And so we need to have a age of the stars. And one tracer, the very good tracer, is Mira variables. And because the Mira variable is very bright, and also they have a period age relation. And again, my colleague in UCL, Jason Sanders, and summer student at that time, he's now a PhD student in Cambridge, Hanian Tan. They recalibrate this age period relation of the Mira variable stars and using Gaia data. And now we have a very nice indication, sort of calibrated data with a period and age relation. So once we identify once we identify the variable stars in the nuclear star disk and see that in the distribution of their age, then we can identify the age of the nuclear star disk. And but as you can see, the period of a nuclear star disk is like a couple of years sometimes, and it's very time-consuming to find these Miras. And although the JASMINE launch is 2031, we need to have a catalog of these long variable stars. So we are now working with the people in the University of Osaka University, and they have this prime telescope in South Africa, Sutherland Observatory, and and they are mapping the stars in the Bauge region from the ground. So their data will be quite precious data to identify these long variable stars. And so we will have a catalog of the Miras before JASMINE launch, and we can see that in the promotion parallax of these stars from the JASMINE. And once we do that, and we can do that, and we can find the age of the nuclear star disk. And this is again simulation done by the Junichi Baba, but like a prime telescope, seeing that lots of Miras, but these Miras can be Bauge Miras, may not be associated to this nuclear stellar disk, which is a cold rotating disk. And so then this red curve showing that, and if it only had a spatial information, we may count many, many Bauge stars as the nuclear stellar disk Mira stars. But the truth is when the bar form is here this time, and then this blue curve is in fact identifying that in the Mira star as a nuclear stellar disk stars from the kinematics. So the adding a proper information like JASMINE can correct this kind of bias of the selection of the nuclear stellar disk stars. So the having this kind of astrometric information really helpful to pin down that formation time of the nuclear stellar disk. And this is also demonstrated by my colleague Jason Sanders in a 2023 paper. And also in the simulation is done by the Junichi Baba. And but some of the people still doubt that it's a really NST in the Galactic Centre, because this is a very highly extinction region. And for example, this Dokari et al. Paper claimed that maybe this is just a part of the Bauge. And so we really need a distance to the stars. Otherwise, people keep claiming that NST doesn't exist. So that's JASMINE also can solve that. The parallax is basically absolute solution for the age, and nobody argue with that. And getting a distance of these stars in the Galactic Centre and really prove that these are in the center of the galaxies is really, really important. And only JASMINE can do this. So we can finish this debate. And also, always exciting thing is the black hole. In the second topic, in the JASMINE will provide all the proper motion and parallax to these near infrared bright stars. And we now have a black hole identified in, of course, in the center of the galaxy. We have a 4 times 10 to the 6 solar mass black hole there, and went to the Nobel Prize because of their heroic effort in 20 years of observations of the stars around the black hole. This is also astrometry. And also the gravitational wave people find that in a black hole around 200 solar mass, and but there is no or lack of the confirmation of the intermediate mass black hole, which is 100 solar mass to the into the 5 solar mass black hole. And yeah, it's pleased to see that people are in this high-level area made a very great effort, and now found the 8,000 solar mass star, black hole in the center of the Omega Centauri, the largest global clusters. That's excellent, exciting things. So it seems they're proving that intermediate mass black hole exists. In probably this is also center of the galaxy because it's Omega Centauri is the global clusters, but this could be a nucleus of the cluster. So the nucleus of the galaxy, Milky Way, may also have more intermediate mass black hole as well. And JASMINE can provide that the information in motion of the stars in the center of the galaxy. And so one way to find that is as Gaia did for the black hole 1 and BH1, 2, 3. And you can see that and how they stars around this black or nothing there, and but stars something rotating around some no bright stuff, and then you can tell that what is the mass of this black stuff, and that is if that is heavy enough, only black hole can do this. And in fact, in the center of the galaxies, you can see that you can have this kind of black hole merger in the runaway collapse, and also the remnant of dwarf galaxies fell into the galaxy in a long time ago, maybe still exist. And then we can detect other intermediate mass black hole. So the Galactic Centre is an interesting place to look for this kind of black hole. And our colleague also predict that maybe 30 or so non-interacting. Non-interacting means it's not accreting gas and bright in X-ray, but their orbit is wide enough not to touch the black hole, but only astrometry can detect the black hole from this motion. And another exciting thing is because JASMINE will provide astrometric information, so that if microlensing happen, so the microlensing is if the stars in behind, they are moving and they pass some small mass object. This case is like a planet, and but then they will get they get brighter by the lensing effect, and but they also that time is also light bends as well. So the stars coming from this way, then that time stars see slightly left-hand side, and but when they stars pass this lens, and then they will see the right-hand side. So you can see that effect, the slight shift of the position of the stars and the delay of the light bend, delay due to the light bend, and that will tell us quite a pinpoint of the mass of the lens. And for example, if the black hole made this microlensing, and we call this shift of the center of the source is a astrometric microlensing, and if we could measure that accurately, then we can really tell that the mass of the lens quite well. Sorry, this is a black hole. Okay, so if this is a black hole and its mass is big enough, like a 1,000 solar mass, and then the distance is around the galactic center, and then the event like this will take like 700 days. And JASMINE is steering the galactic center for 3 years. If that event happened in a part of that, we can really tell that this centroid shift. And in fact, if this is a source is big enough, like 1,000 solar mass, then the shift is 8.2 2 milliarc seconds, which is very easy for JASMINE to look at that. So we may be able to find that kind of black hole from the either or both this binary effect or astrometric microlensing effect. And not only JASMINE is steering the center, but in Japan, we are also planning to have the wide field adaptive optics in a near infrared detector in the Subaru. So we can observe in the same time with the JASMINE, and then Subaru can use a JASMINE as a reference frame, and then they can do a better astrometry than you can do only by Subaru. And then we can do the same thing using this much deeper data with the Subaru Ultimate. This is the instrument. And then another interesting things, of course, it's always a big elephant in the room in astronomy. Astronomy is a dark matter. They exist, but we have no idea. And in fact, the candidate of a dark matter particle is still a big parameter space and 10 to the minus 22 electron volt to the solar mass black hole. So we don't know which one is really the dark matter. And yeah, of course, it's a normal one, like a cold dark matter. It's like a WIMP and in like a Jebel area, but still nobody really found it. So that excited lots of people think about the primordial black hole, or even go to the ultra light dark matter, like a 10 to the minus 22 electron volt. And in that regime, if you have a dark matter halo, and you need lots of particles. So it means that you really need to pack the particles in a very small place to really make that a high density area like a center of the galaxy. And then the Bose-Einstein condensation happens. So you cannot really, the quantum pressure basically prevent you to collapse. And so basically the Broglie length is getting the bigger than a mean free path, and then you cannot really squeeze. So you get the core of the dark matter in the center of the galaxies, like this simulation shows. So Milky Way, if it is the ultra-light dark matter, the real dark matter, we would expect that we have this large core, relatively large core in the center of the Milky Way. And that size is related to the mass of the particle. So if it's a bigger, it's a smaller mass, like 10 to the minus 16, then they have a very small core. And but if they are very small mass particle, and then you have a much bigger core. And this is the nuclear star clusters expected density. So it's a dark matter density due to this core can be comparable to the stellar mass. So looking at the kinematics of them, and then you can infer the density of the dark matter. And you can probably confirm or reject in this area by the JASMINE astrometric information. And then you can reject that and tend to reject or confirm dark matter mass between the 10 to the minus 19.5 to the around 10 to the minus 21 or so. So this one, I think 10 to the minus 22 is probably what we are hoping to reject or confirm. So JASMINE can confirm or reject an ultralight dark matter. That's one of the interesting candidates. And also, we shouldn't forget that it's a JASMINE is looking at the galactic center like this, but there's lots of data between the sun and Earth. And so we can use that, and the kinematics and the parallax is available for these stars. And looking at the kinematics of them, then we can also infer the dark matter mass or density as well. And so this is the result from the Gaia, looking at the galactocentric radius versus the rotation curve, and this total mass. So you can infer from the rotation curve the total mass of the galaxy. And we can see that very nice constraint from Gaia, but it's up to 5 kiloparsec or so. From the inside, as I said, Gaia is not very good to probe that. And in the kinematics, especially in the galactic midplane. And so, but this is the missing data we can provide by JASMINE. And also because this area is quite important, and then we are looking at the density distribution with the radius versus density. And if the cold dark matter model predicts that there's a cusp of the dark matter in the center of the inner region of the galaxy. And there's some other people talking about maybe a core of the dark matter can be created depending on the nature of the dark matter. So we can distinguish the core or cusp in this inner region where the still Gaia data is missing. So the JASMINE could provide the key information of the nature of the dark matter as well. And the final topic of the astrometry is this nuclear stellar disk is in fact a similar size to the galaxy we see in the JWST in the high redshift galaxies. And this is suggested by some Ouchi in NOJ. And this is showing that the stellar mass versus effective radius of the galaxies around us, the elliptical galaxies and dwarf galaxies and dwarf spheroidal. But it's also they plot that in this redshift 6 and 7 dropout galaxies. They are in this size, and the nuclear stellar disk of the galaxies, in fact, this size. So it's a couple of hundred parsec and 10 to the 8 solar mass or 10 to the 9 solar mass. So this is basically the similar mass, similar size and mass to the galaxy in the high redshift we see that. So there may be some remnant because the Milky Way should start from somewhere and from the very small. So we can see the beginning of the Milky Way formation in within the nuclear stellar disk. So the nuclear stellar disk may be telling to be important information, could provide important information of the beginning of the formation of the Milky Way. So that's all exciting things I could say about the Milky Way. And of course, these data, as Gaia showed, and astrometry data can provide all the information, not only for the galactic studies, but also the high energy astrophysics and the star formation, and also exoplanet. That's how we can provide that information too. But we also have this a second goal for the exoplanet, which is we can do that this from the transit observation. And okay, so this is suggested by our exoplanet science team led by the Hajime Kawahara. And because the Galactic Center is this direction, and we are rotating around the sun, and we are also JASMINE is the low Earth orbit and the sun synchronous orbit, and this red one is JASMINE's orbit. So we can only see the Galactic Center in autumn and spring. So we have 6 months of the time we cannot really see the Galactic Center, but we can, of course, we do the science. And so the team by the Hajime and led by Hajime suggested that we can observe, we can stare the M dwarf and finding that the transit in a galactic, habitable zone in exoplanet. And there's a M dwarf everywhere. So this is the sky map, and this white one is the M dwarf candidate we can observe. And this region cannot really observed because of the Galactic Center region. So we spent the time, but it's avoiding that. We can see that we can stare these M dwarf for a couple of months and or weeks and months. And it's a good thing in this near infrared mission, like JASMINE, is M dwarf. It's a small red galaxy, red star. Is the spectra is like this, and other current exoplanet missions use the optical filter and TESS and KIOPS and etc. And but JASMINE really, take that kind of peak of the flux from the M dwarf. So this is quite a suitable filter we are using for the using in JASMINE, but it is very suitable for the transit observation for the M dwarf. So the idea is, we have a star, and then if we have a Earth-like planet, go front of the stars, and then we see the slight dim of the light, and we try to detect that. And M dwarf is like a 3000 K, and it's very small and very small mass. And but near infrared photometry can give us that, and 0.2 and 0.3% of the photometric accuracy. And the habitable zone orbit will be like 2 weeks for these small star. So the habitable orbit of sun is of course like around the year, which is very difficult to monitor. But these small stars it's a very short time, so it's feasible for the satellite mission. And yeah, this is the simulation done by the Ryuki Hirano, and these are what you can get from the accuracy of the photometry from the JASMINE data, JASMINE-like mission, and then we see that this kind of transit if we find if we get this kind of data, the monitoring of these stars. And this we are going for the niche, and this is the x-axis distance from the stars. And if the exoplanet exists like sun, sorry, Earth around the sun, like one solar mass, and this is the y-axis, the mass of the host stars. And then this is the like Earth, it's a 1 AU in orbit, and it's now that the ground-based telescope and Spitzer found the TRAPPIST system around M stars, and they also cover the habitable zone exoplanet. Sorry, this is what the habitable zones are in a different mass of the stars. So the Earth should be covering that. And then, TESS also found that this TOI 700 this is also the space mission with NASA. And of course, it's NASA's flagship, and the Roman will launch, and they basically try to find that Earth-like planet. And then JASMINE can basically target to the stars between the TESS and the ground base, and using a 36-centimeter telescope in this near-infrared region. But we are not doing a survey of that stars like a TESS does, but we need to target, and because our field of view is very small. And so the idea is basically we will rely on that ground-based telescope find some exoplanet transit or radial motion, maybe the exoplanet transit in the inner orbit, like a smaller period exoplanet. And then JASMINE will follow up that and stay there for a month or so and try to find a couple of weeks period exoplanet in the outer region of this stars, which is already exoplanet is found in the inner disk of the planet. So this is done, in fact, in the TRAPPIST. They found that this ground-based one is found at this inner planet, and then they found Spitzer basically follow up, and then they observed, they found an outer disk planet, which is in habitable zone. So that is a strategy we can make, and we hope that in a couple of Earth-like habitable zone planet can be found by the JASMINE, and then we can follow up with Ariel or JWST if they're going. And also that not only the targeting M-dwarf, but we can, because the JASMINE has a much higher spatial resolution than TESS or Skeops, and so we can also look at the stars in a cluster, like a dense stellar region. So this is like M39, and you see lots of stars, but one shot of the JASMINE, like 0.6 degree, times 0.6 square degree field, there's lots of stars. So you can get, by monitoring this region, you can get photometry, time series photometry for free for many stars. And so then you can find some of the stars. So this is the longitude and latitude distribution of the star cluster. And each star cluster, depending on their size, we can find like Earth-sized planet, this blue, the size of this, and more than like 1,000 stars in this big one, and also Neptune-sized planet and more than 1,000. So we can find many star planets in the star cluster as well, so which is not available from Kepler or TESS. And of course, we have astrometry, so we can find that astrometric planet, especially in the Galactic Centre region. We have 3 years of data, and but you can also see that in a exoplanet in like ultra cool dwarfs, very small stars, and we can tell that if or not they have a giant planet or not. And also, yeah, it's radio velocity also telling us that some of the exoplanets exist in some of the stars, and but it could be a very long period system. But it's yeah, Gaia also already monitoring some stars, so that we can combine the Gaia data and the JASMINE data. We can monitor the astrometric motion for the more than 20 years. And also the astrometric microlensing may happen very, very close to us. And then we can really see that in microlensing for the, for example, free-floating planet. And also the 3 years of Galactic Centre survey basically covers all of this. And using this data, you can find or trying to explore that this kind of thing is happening in a Galactic Centre region. And it's now, I'm just conscious of time. Okay, okay. So now using the last 5 minutes, I just show that in our preliminary design of the JASMINE. And so the JASMINE is a spacecraft like this, and then there's a telescope like that, and the light bent 5 times and getting this detector in a near-infrared detector. And for the astrometry, it is important thing the stability of the telescope and optics. And we use this super imber, which doesn't bend or move, and even if the temperature change a bit. And so we keep the temperature here, but also use this special material. It's quite resistance to the temperature change. And also mirror is very important, not to change form, shape due to the temperature change. And also that we keep that the temperature of the detector box and this telescope box as well. So that's quite the key point of the astrometry telescope. And we use the near-infrared detector made in Japan and developed in the National Astronomical Observatory of Japan. And we do the 2x2 mosaic of these 2K by 2K detector and cover 0.5 degree in across. Okay, and yeah, so we are doing that and also start simulating that by the Ryo Osawa here. And we do that on all the usual things and end-to-end simulations. I will try to go faster with this. And yes, we are now proving that basically that we can achieve this kind of level of the astrometry at 25 microsecond from the more realistic image in the Galactic Centre. So the JASMINE is coming and launched in 2031, and will provide you all the interesting information in the region of the Galactic Centre. And this is a new project in Japan. We need more people. And so that's why we are here. And it's exciting time and exciting mission. And so if you're interested in, please join us. And you're very, very much welcome to work together. And also that the timing of this is interesting for the maybe future early career audience. They did JASMINE the 2031 and Gaia-near, we keep talking about that. And this is expected in 2045 or maybe later. And also the stellar seismology mission is, we are suggesting Hayden. It's coming in 2040, and we suggest for the ESA M8. And this is a mission, astroseismology mission, steering one of the several globular clusters for many, like 18 months for 47 TAC, Omega-7 for 6 months. And but the resolution of the pixel is much, much smaller than the Plato Kepler. And so that we can really see that in stellar seismology for the globular clusters. And that will give us a calibration of the age. So that's quite important mission for the stellar physics. And stellar physics, stars are very important tracer for the galaxy or exoplanet or anything. And ultimately, we are, so the JASMINE will be the frontier or hopefully the pioneer to the near-infrared astrometry. And then the Gaia-near is the all-sky Gaia-like astrometry mission. And we'll go down to the 20 magnitude in the H band and provide a similar accuracy in astrometry in 10 microsecond. And also the proper motion, you can get like a microsecond level. So exciting time is coming, and hopefully JASMINE will be a kickoff of this near-infrared astrometry. So thanks a lot for listening. Thank you.
Well, Well, thank you very much, Daisuke. That's this glimpse into this very exciting infrared future in front of us. I invite questions from the audience online. Please raise your hand or type into the chat. And also, of course, from the audience, starting with any student questions. One student question here.
Hi, a really nice talk. Thanks for that super nice overview. I didn't know this mission, so really cool.
Yeah, thank you.
Yeah, I'm a PhD student. I work with massive stars. And the question I would have is because you mentioned at the beginning that this JASMINE would sort of do things that Gaia didn't do. And I wonder if, yeah, because there are lots of luminous stars which didn't got parallaxed by Gaia. So I wonder if JASMINE would get parallax of them, like luminous massive stars that were not measured before.
Yeah, that's an interesting point. And yeah, surely that also JASMINE is a step and stair mission, and it's depending on the integration time. We can, of course, cover that in the bright stars as well. But at the moment, to cover this galactic center field, we try to integrate 12 seconds or so, and we saturate some of the bright stars. So that depends on the requirement and depends on the interest. We can probably also we can do the non-disruptive reading as well. So then we can shorten the integration time for the bright stars. So if we have a telemetry capacity and etc., then we can also cover the bright stars as well. And so it's possible, but it's not targeted yet. And also the massive stars, because the filters are very red. So I don't know how much massive stars we can find. But at the extinct region, especially in the midplane, we probably see that some of the star forming regions as well in this area. And that is probably quite interesting source region to look at for the massive stars. Yeah, thank you.
Another student question, Subi Sentinel Kumar.
So thanks very much for the nice talk.
Okay.
So in the payload slide, you mentioned that the gallium arsenide complex is used to detect the near infrared.
The detector, you mean?
Yes.
Yeah, that's a good eye. This one?
Yeah.
Yeah.
So could you please explain how this complex can detect?
So indium gallium arsenide.
Yeah.
Yeah. So apparently, I'm not a detector specialist, so I cannot really tell you much. I have to confess. And but this is a nice, it's the nature of this system, the composition of that, and then they can detect the lights, the infrared lights, and then it produces electrons. So that's you need this kind of special material to really capture that kind of photon. And but it's so far this kind of material can go up to 1.6 micron. And you may see that MCT and like Hawaii telescope, Hawaii detector, which is used for the many other missions or ground-based telescope, they can go up to many, like 22.4 longer wavelengths. But yeah, this one can only go up to 1.6 micron. And we, in the NLJ, we only have this technology to do it. So that's one our limitation. But 1.6 is near infrared enough. So we are trying to do this because it's made in Japan. We know the characteristics. We can test as much as we can. And the near infrared detector is now basically made in the US. And there is a lot of restriction to do anything, and also very expensive.
Okay, thank you. I see we have one question already from the online audience, so I'll proceed to that. I'll read it out for the benefit of the audience here. It's from Hans-Walter Rix. Hans-Walter writes, "Thank you, Daisuke, for this exciting talk. I have a question about the other mission context of JASMINE. For example, the Roman Space Telescope is planning to look at 7 fields near and preferably also towards the galactic center hundreds of times over 5 years, starting in 2027. They claim to get precise parallaxes and proper motions from this. Does that impact JASMINE's science case?
Yeah, thanks, Water. And yes, that's of course the obvious question and the big elephant in the room as well for JASMINE. Oh no, we talk about big elephant. And yes, the Roman is exciting mission, and both for the exoplanet and also they do the galactic bulge center survey, as Hans Water mentioned. And they claim that in a parallax, parallax accuracy is it's there. I think it's like a Gaia-level, 10 microsecond or so. But we still don't know that they are the general purpose of the battery, and I don't know how much time it will be spent for the bulge survey. Maybe Hans Water may know much better. And also they are not using a special careful material or careful telescope structure to control that and systematic effect, which is very important for the astrometry. So even Gaia had lots of surprise that like a mirror is bending, but thanks to the monitoring of this basic angle monitor, they could calibrate out and get this microsecond accuracy. But so we slightly doubt that because this is not, Roman is not a special mission for the astrometry, so that you never know that if or not they can achieve it. And that could be a big question. And we hope that the Roman can also provide us quite interesting information, especially proper motion. They can do it. But I think parallax is probably the one thing that JASMINE can provide. And also maybe hopefully the synergy with Roman and JASMINE, we should really look at the same field as well, so we can cross-calibrate this kind of information too. So that's our hope.
Okay, so the answer appears to be superior positional accuracy with this dedicated mission.
Stability,
stability.
Stability, because if telescope move and then the image distort, and that's very difficult to correct.
Okay, well,
even Gaia, people spent many years to do it.
Okay. Then we'll move on to the questions from the audience here. I see two. First of all, Yufeng.
Thanks for a nice talk. Now, this is a question in the field of astrobiology. So is the habitable zone defined such that the average surface temperature of a certain planet is between 0 degrees Celsius and 100 degrees Celsius, which are the melting point and boiling point of liquid water under standard atmospheric pressure on Earth?
Yeah, so I think that's probably a habitable zone definition is also coming from that as well, right? Yeah. So I think that you're right, and that definition keeps changing as well. And but I think it's important thing is that you really need a couple of weeks of observation. So yeah, thank you.
Okay, another question.
Thank you for the really nice talk. I think stellar archaeology in the Galactic Centre is a big topic for this mission, but I think your talk mostly focused on the kinetic part of this. Can you comment on the ability of JASMINE in measuring the chemical balances of the stars in the Galactic Centre?
Yeah, that's a very good point. And JASMINE is a photometry mission and one band, so that you cannot really get any chemistry information purely from JASMINE. We don't have a spectrograph or anything at all. But this is a Japanese project, and we have a Subaru in Japan and Mauna Kea. You can still see the Galactic Centre, and these are very bright stars. And we have this prime focus spectrograph, which is thousands of fiber, can look at in a very large field of view. So we can map this all JASMINE stars in I think I forgot how many days, but we can do in not couple of days, but a reasonable time of the nights. And so you can do that, get a spectra. And then you can do the chemical composition and FeO by H and alpha, and also effective temperature of stars. So we can do that and kind of information. So you will get, so Japan will provide you that, and if also you can join, and we will provide that in a chemical composition, radial velocity, and also proper motion and the parallax of all these stars. So that, yeah, so we have we will follow up with the Subaru.
Okay, I think we have time for one last question from here.
Thank you for the great talk. This is Arya from the Max Planck Institute. So you talked about using the nuclear stellar disk to understand the epoch of the bar formation and also constraining the dark matter mass.
Yeah.
Could you elaborate a little bit more on how that would help us understand the slowing down of the bar and how that compares with lambda CDM?
Yeah, that's a very interesting question. And yes, in our paper, we talk about that. And but yes, so bar is I think I should credit my colleague Ralph Schonrich and Limpe Chiba did a nice analysis of the Gaia data, and they claim that galactic bar, the pattern speed of galactic bar is slowing down, and they found that from the kinematics in our solar neighborhood, which is measured very precisely by Gaia. And what happened in the Galactic Center, that's quite interesting part, and I'm talking to Ralph as well, and Ralph is also quite interested in that kind of a topic. And what we expecting is if they, the resonance of the bar, the size of this nuclear, especially this nuclear stellar gas ring, the formation area of the stars, we have this central molecular ring in the Milky Way. And that size is probably changed with the pattern speed because of the resonance. So if we could see the distribution of the age of the stars in the nuclear stellar disk as a function of the radius in the nuclear stellar disk, and then that could be we can infer that if or not this size of the nuclear stellar disk getting bigger, which can also infer that and bar is getting longer, and so then the resonance is getting outside. And but of course, there will be a lot of degeneracy in the parameter, so we can compare that with the numerical simulation, and that again the fun part starts. And but it's, yes, surely we really want to do that. Thank you for that question.
Okay, well, before we thank, time is getting on. I just want to make a couple of announcements before we thank Daisuke. And the first is next week's talk will be from Tadafumi Matsuno from Heidelberg, and he's just here in the front. So do come along, and he'll be talking about something which is, I guess, not that far away, but we'll look forward to that very much. And then this evening, if I can just move to the next one, we will have directly following the colloquium informal drinks for students at Hemingway. So if you're interested in joining, please gather at the front. And so who's organizing that? Yeah, hi, thank you very much. Yeah, just to come along and announce yourself. So, and then later on, 7 o'clock, coming back across the bridge to the Dorfschenker for dinner. So anybody wants to join, please also announce yourself at the front here. So thank you very much, Daisuke. That was a fantastic information about this very exciting future, lots of rich physics, and we wish you all the best in your endeavors. And we look forward to hearing about this maybe in maybe another eight years or so.
Coming,
okay, thank you very much.
Yeah, thank you very much.